Hello friends, welcome you all in B.Sc Electronics class. This is second lecture, this module 1, T.Y.B.Sc semester first, Advanced Digital System Design, paper first. The topic 2, second lecture, Mealy and Murray state machines and state machine notations in digital sequential systems. So let us start. First, we'll see the general form of sequential circuit, its block diagram, and working in short. Here, the block diagram of a general form sequential circuit is shown. It includes basically three blocks. The first is combinational block. The second is flip-flops or memory, and third is again the combinational circuit, which is output logic circuit. So such three blocks are there. W is input to the input logic block. This combinational circuit block is also known as input logic block. The another input to this combinational circuit is taken from the output of flip-flop, that is Q. This is the output of flip-flop is also known as the state of the machine, is given as one of the input this input logic block for this combinational circuit. The output of combinational circuit, this one, is nothing but the excitation input to this flip-flop block or the memory block, and another input to that memory is a clock input that we know the flip-flop works on. The clock input, that is, it must be given either type of clock signal, that is maybe the level triggered clock or age triggered clock. So that clock must be there, and it produces the output that is called state variable or the state of the machine, and it is given to the this combinational circuit is the output circuit block or output block. The another input to this output logic is given from this input shown by blue line. In all circuits, there is no need to have this input provided for this combinational circuit. This circuit produces the output Z. The short description of the circuit is given here. The combinational logic that provides the input signal to the flip-flops has two sources. That is what we have described. The primary input W, this one, and a present or the current state of flip-flop Q. Q is called present state or the current state of the flip-flop or the sequential machine. Thus, changes in state depend on both the present state and the value of primary input. Is the present state input and value of primary input. Figure indicates that the output are a function of present state of the flip-flops and the primary inputs it is given. Although the output always depends on the present state, they do not necessarily have to depend directly on the primary inputs. Thus, the connection shown in blue in the figure may or may not exist. Which one? This one. This may or may not exist always. Depending on whether that input is given or not, there are two types of sequential machine, a Mealy sequential machine and a Murray sequential machine that we have to study this lecture. The sequential circuits are also called as finite state machines. Short, they are called as FSM, and the name FSM derives from the fact that the functional behavior of the circuits can be represented using a finite number of states, or we can say since there are finite number of states the sequential machine goes through. Therefore, such machines are called as finite state machines. So, we'll see the two types of sequential machines, a Mealy sequential state machine and Murray sequential state machine. Here, first of all, we'll see Mealy sequential state machine. Here is the block diagram of Mealy sequential state machine. See, there are again three blocks. That block diagram we seen in the beginning of the lecture. The same blocks are there. The input logic block was named as a combinational circuit there. Input logic block shown by a letter F. The output of input logic block is excitation input E or excitation variable E, which is given as the input to the memory, and another input to the memory is clock. Memory maybe it contains the flip-flops, number of flip-flops may be there. The output of memory is the state variable S, and it is given as input output logic block named as G. So, in a Mealy sequential state machine, there are three blocks: input logic block, memory block, and output logic block. The input logic block has two input. One is input variables I, and another input is the state variables S. The input logic block generates the excitation output E for memory. The another input to the memory clock which generates the next state output, and this state variable output is given as a input for generating the output final output that is given to the output logic. And in a millisequential state machine, the another input to output logic is given from here, that is input I. So the output logic has two input, one is state variable input and another is input variable I. So taking these two inputs into consideration, it generates the proper output is shown by letter O, output variables O. So this is a Mealy sequential state machine. Three blocks: input logic block, memory block, output block. Input logic block has two input variables. One is input variable I and another input is S. Generates the excitation output, gives to the memory. The another input is a clock input, generates the state variable output given to the output logic G, and another input is I, press the output variable. The logic function shown in the model translate Input and flip-flop output information. Input logic produces excitation input to the flip-flops. The external input variables I and state variables S applied to logic function G generate output O. That's what I have discussed. Okay. The next is Murray sequential state machine. This is another type of a sequential machine. The basic difference in a Mealy and Murray sequential state machine is only of his connection. Here it is shown by dotted line, and in this bracket what is written there? Dotted line indicates no connection. Means what? The input variable I is not given as a input to this block output logic block. So the output logic block G has only one input, and that is a state variable input S. Depending on that input, it produces the output variable O. That is only the difference in Mealy and Murray sequential state machine. The student should take into consideration the difference in Mealy and Murray sequential state machine. In a Mealy sequential state machine, the output logic has two inputs. One is from input variable and another is from memory, that is state variable S. While in this Murray sequential machine, the output logic generates the output depending only on state variable S. Okay. Mealy sequential circuit differs from Murray sequential circuit in the variables used to generate the output function. Okay. The input logic produces excitation input to flip-flops. This one, excitation input to the flip-flop. Murray circuit output is dependent only on state variables S. Yeah, output depends on state variables S only. Some key points are taken here. Just quickly go through these key points. The digital circuits composed of combinational and sequential logic sections are generally described as finite state machines. A machine is synchronous when the state transitions are controlled or synchronized by a clock signal. The synchronous machine definition is given here. Machine is said to be synchronous if the state transitions are controlled or synchronized with a clock signal. A machine whose operation is not dependent on a clock signal is said to be asynchronous. That is what the distinction between synchronous machine and asynchronous machine. Some notations are taken here. The present state, generally known as PS, of the state machine is determined by the variables stored in the flip-flops of sequential section. Present state and the next state NS of state machine is defined by the circuit of combinational logic circuit section. That is a next state. The difference between Mealy and Murray sequential machine model, in most of the time in examination also this point is asked, differentiate between Mealy and Murray sequential machine. So you should know the basic point of distinction between the Murray state machine and Mealy state machine. That block diagram we already have studied. The Murray state machine, the state machine output depends entirely on present state. Murray state machine that we have seen, and Mealy state machine. The state machine output depends on inputs and present state. This is the most important point of distinction between Mealy and Murray state machine. It must be noted that there are also hybrid machines with some outputs being of Murray type and other of Mealy type, means a mixing of Mealy and Murray type machine is present in some of the hybrid machines. Therefore, they are known as hybrid machines. A machine always has a finite number of states. Therefore, they are known as finite state machine. For n variables, the machine must have two raised to n state. If the number of variables is n, then the relation between number of state and number of state variable is given by 2 raised to n. A machine is defined by specifying the number of inputs and outputs, the initial state, present state, and next state. Any machine, any sequential machine specified using these number of terms, the number of inputs the machine has and the outputs it has, the initial state, present state, and next state. Considering this term, we can describe any machine. Now, the state machine notations. While describing or studying the various types of sequential state machines, we always see or observe a number of terms in that machine. So, we should know what are exactly these terms used in the sequential machine to describe the sequential machine. First is input variable. The all variables that originates outside the sequential machine are input variables. Originating outside the sequential machine, all these variables are the input variables. Then the output variables. The variables that exit sequential machine are said to be output variable. Then the state variables. The output of memory, that is flip flop, defines the state of sequential machine. That is, the flip flop outputs are called as the state variables. That we have seen the Mealy sequential state machine, Murray sequential state machine. The memory output or a flip flop output turn as a state variable S that represents the state of that sequential machine. So these variables, they are called as state variables. Then the excitation variables, these are nothing but the inputs to the memory, these flip-flops. These variables excites the memory to change. Therefore, they are called as excitation variable. The state variables are the functions of excitation variables that we have seen in the block diagram of sequential machine. The output of input logic circuit generates the excitation variables, and these are given as an input to the memory. So they, since they excite the memory or they cause the memory to change, therefore they are called as excitation variables. Then the state, the content of memory, called the state of sequential machine. The state variables and states are related by expression 2 raised to x equals to y. the number of times question is asked on this relation relation between state variables and the number of state. The relation is 2 raised to x equals to y, where x represents the number of state variables, or if x is the number of state variables, that is number of flip-flops actually, and y represents the number of possible state. So if there are x number of state variables, so the number of states possible in that machine is 2 to x equals to y. Here you can take an example. If there are two state variables, that is x equals to 2, then the number of possible states 2 raised to 2 equals to y, therefore y equals to 4. If there are 4 state variables, then the number of states possible is 2 raised to 4 equals to 16, that is y equals to 16. Now, the next is present state. Again, the state machine notations are continued. Present state, that we have already seen. The status of all state variables at some time before the next clock pulse to occur, or before the application of next clock pulse, represents a condition called present state, or in short we can say the status of state variable or the memory before the application of clock pulse. That status is nothing but the present state of the memory or the machine. The next state is what? The status of all state variable at some time t plus 1 is after the application of clock signal, represents a condition, and that is called the next state. The state diagram. The state diagram is graphical representation of a sequential circuit. Individual state. Now, how to draw the state diagram of a particular sequential machine? So, while drawing the state diagram, individual states are represented by circles with an identifying symbol located inside. Here, a state machine of D flip-flop is shown in the state diagram. So, the states are shown by the circles. They are the state, and the state may be either 0 or 1. So there are two possible state in the flip-flop. The output state may be 0 or it may be 1. 1 is nothing but Q and 0 is Q bar. So states represented by circles with identifying symbol located inside, just written here. Changes from state to state is indicated by directed arcs. The change from one state to another state is represented by these directed arcs. Directed arcs means they are shown by these lines with arrow. They are called directed arcs. The input conditions that cause state changes, or that causes the state to change, and resulting output signals are written adjacent directed arcs as they are written here: d equals to 1, d equals to 1, 0, 0. So the state or input condition that causes output to change written here, and the output is also written on the same line by putting the slash, and after that we can write the output here. It is not shown. Next point, or in next lecture, we will see how the outputs are written. In the syllabus we have to see or learn number of such state machines. So with the time come there. So just we will go through how the state diagram actually be drawn for a flip-flop. Here the truth table for D flip-flop E1. We know the truth table for D flip-flop. The clock is applied. Input is 0, output is 0, and if input is 1, output is 1. Now see, we'll start with suppose presently the flip-flop output is 0, and if input is 0, that is D is equals to 0, present state output is 0 and input applied is 0, so there will be no change, it will maintain the same state. So we have drawn this blue line arc, there is no change. If presently input is output state is 0 and input is equals to 0, it maintains the same state. But if in present state output is 0 and input D is equals to 1, we know if flip-flop D input is 1, that's the flip-flop or it makes the output 1, so it changes to 1. Therefore this directed arc line is drawn to show the change from 0 to 1. Now if presently present state output of flip-flop is 1, input applied D is equals to 1, will maintain the same state output. Since it is already in one state, output is 1, will maintain the output. But if presently output is 1, input D is equals to 0, will change the state, will go to 0 from 1. So in this way we can understand the state diagram of D flip-flop. Next is state machine, state table, sorry. What is mean by state table? State table is a tabular form of state diagram. The present state column lists all possible states in the machine. This present state column. The all possible states are listed in the machine, and state table indicates the state transition. Here, one example of a sequential machine is taken whose state table is written here. What is number of things present in the state table, or how we describe the state machine in the tabular form, is given here. It contains the present state, so the number of states that state machine are listed here, and next state and output. So here there are next state shown by these two letters xy, and output is shown by letter z. So if present state is A and input xy 0 0, y is 0 0, the output is A. Next state is A and output is 0. See again, present state is A, input xy is 0 0, then the next state is A and output is 0. Similarly, if present state is B, input is 0 0, next state is B and output is Z. Again, the present state is C, input is 0 0, next state is A and output is 0, and the present state is D, input is 0 0, next state is A and output is 0. Similarly, here in the present state is A and input is 0 1, next state is again A, output 0. In this column, if the present state is A and input is 1 1, next state is B and output is 0. Here, present state is A and input is 1 0, next state is B and output Z is 0. So in this way, all possible states are listed in the state table or machine, presented completely in the state table. So it is the tabular form of state machine represents the state machine. Tabular form is state table. Transition table, it takes the state table one step ahead. Creation of transition table requires that specific state variables values to be assigned to each state. So in the transition table, the proper state assignment must be done so that we can represent the transition table of the state machine, just like here. The inputs are represented with these state assignment 0 0 0 1 1 1 and 1 0. So the proper state assignment must be done so that it is easy to represent the transition between the state. The assignment of values to state variable is called state assignment. Assigning the unique value to state variables is called state assignment. The transition table illustrates the changes that occurs the state variables as the state machine sequences from one state to next state. The excitation table and excitation equations. What is the excitation table? It shows the minimum inputs that are necessary to generate the particular next state. The excitation table for any state machine M is exactly same as its transition table. If D flip-flop is used to realize the circuit, here particularly if D flip-flop is used to realize the circuit, then its excitation table and transition table, they are same, is given. The excitation equations are derived directly from excitation table. Here the table for D flip-flop is given here. Here present state, next state and input D. Now, if the present state is 0 and input D is 0, next state is 0. Again, if the present state is 0 and input D is 1, the next state is 1. Present state is 1 and input is 0, next state is 0. If the present state is 1, input is 1, next 1. So, the excitation equation or the characteristic equation for D flip-flop Qt plus 1 is equals to D. It is written directly from here, input and next state. If D is 1, next state is 1. Therefore, and if D is 0, next state is 0. Therefore, Qt plus 1 next state output is directly depend on D. That way, it is written. Here, the state diagram and state tables of remaining flip-flops can be studied. Here, the first is SR flip-flop. Its table is given here. Input, present state, and next state. We know the SR flip-flop table. In SR flip-flop, its input is 0 0 and present state output is 0, next state is 0. And if the present state output is 1 and input is 0 0, next state output is in 1. It maintains the same state under input conditions 0 0. So when SR input is 1, S input is 1 and R input is 0, then if the present state output is 0, next state output is 1. So flip-flop gets set. And if under same condition, if present state input is output is 1, it maintains the same state output, that is 1. When S is 0 and R is 1 and present state output is 0, it maintains that 0, and if present state output is 1, it resets the flip-flop. So under this condition, the output becomes 0, and 1 condition, that is S is 1 and R is 1. This is forbidden condition in SR flip-flop that we all know. So in SR flip-flop, under 0 condition, SR condition, output maintains the same state. If it is 0, 0, then 1, 1, or SR equals to 1, 0, sets the flip-flop, or SR equals to 0, 1, resets the flip-flop. So the state diagram can be drawn here. Again, in SR flip-flop, two possible output state, that is either 0 or 1. Now, we'll considering present state output 0, and if input is 0, 0, the next state is again 0. If input is 0, 1, input is 0, 1, again it maintains the same condition. If SR input is 1, 0, goes to next state because it sets the flip-flop, and 1, 1 is not allowed, so it is not taken here. Now, if presently the SR flip-flop output is 1 and input is 0, 0, then the same state. Okay. If the input is 1, 0, that is S is 1 and R is 0, then the flip-flop gets remains set, and if the input is 0, 1, flip get reset. So in this way we can draw the state diagram of SR flip-flop. Here the JK flip-flop, SR flip-flop and JK flip-flop, the truth table is almost identical except this last condition, 1, 1 condition. All these remaining entries are same. For JK input are 1, 1, and if present state output is 0, next state output is 1. So if it is 0, it change the output from 0 to 1, and if it is 1 presently, next state output is 0. So this condition is called a toggle condition in JK flip-flop under JK inputs are 1. So that is only the difference, and accordingly we can draw the state diagram of JK flip-flop. Here, if the presently output is 0, present state output of flip-flop is 0, and if input is 0, 0, next state is 0. If input is 0, 1, next state is again 0. If input is 1, 0, that is J is 1 and K is 0, or input is 1, 1, the flip-flop gets set or toggles. And if the present state output 2 is 1 and we apply the JK input conditions, under this, if JK input is 0, 0, it maintains the same state. If JK input is 1, 0, again the output remains the 1. If JK input is 0, 1, that is J is 0 and K is 1, it sets the flip-flop, that output becomes 0, and if again JK input is 1, 1, it toggles the flip-flop, it goes to 0 from the 1 condition. So that is what the state diagram of JK flip-flop. Here the state diagram of T flip-flop is given. In a T flip-flop for toggle, if T is 0 and presently output is 0, the next state is 0. If the presently output is 1, next state will be same state. If T is 1 or present state output 0, toggles, it goes to 1 or the output becomes 1. Again T is 1, presently output is 0, 1, so it toggles T. T for toggle, its state diagram is drawn here, starting with Q equals to 0, that present state output Q is equals to 0, and if T input is 0, is the same state. If T input is 1, it toggles the output, becomes 1. If presently output is 1 and T is 0, maintains the same state. If T is 1, toggles the flip-flop, so it goes to 0. These are the characteristic equation of flip-flops. SR flip-flop or SR flip-flop. The next state Q is equals to S plus R dash Q. For D flip-flop, Q plus is equals to D. For JK flip-flop, the equation is Q is equals to JQ bar plus K bar Q. Plus means or K bar Q, JQ bar or K bar Q. And for T flip-flop, Q next state Q plus is equals to T XOR Q. So these are the characteristic equations of basic flip-flops. Thank you.